One of the key components in a laser is the resonator. As we will see, a resonator is simply the set of two mirrors providing the radiation to form inside the cavity and produce the laser beam. To understand better what's happening, we have the following content. First of all, we'll take a look at the so-called mode selection by the resonator. Then we will differentiate between longitudinal modes and transverse modes. We will talk about stability of resonators. That is not mechanical stability, but a principal stability. And last not least, we will look at an example of a laser resonator. The laser principle works such that we have an active medium, in this case here, a crystal which emits photons. If we provide a reflection of the photons at the ends of that crystal in these two positions, then we talk about a resonator already. We provide the pump light to the active medium, and based on the feedback given by the resonator in terms of reflection of the photons, we get as a result the laser beam. The resonator is one of four elements which are necessary for a laser. We need the pump, we need the active medium, and we need the resonator, and maybe some beam shaping elements. In the next view graph, you will see a very rough comparison between the thermal light sources on the right top picture and a laser. As you see, the thermal light source emits all kinds of wavelengths. This is indicated by the different wavelengths here in all directions. And if you want to try to focus thermal light, for instance with a lens, we always get only a very small solid angle from that source, so the efficiency in using this light usually is very limited. However, if we look at a laser, we observe not an isotropic emission, but we observe a directed emission due to the fact that we have a feedback coupling of the radiation into the active medium, resulting in a laser beam. So the resonator basically does three things. Number one, it provides feedback for stimulated emission. So it allows the laser process to start from a principal point of view. Then, as a consequence, we get, so to say, automatically a transversal confinement of the radiation in terms of only this angle, as I indicated here in the sun experiment, in the sun case. Of course, in the laser we only have this type of emission, and due to the omission of all the other processes, the stimulated emission in all other directions, we get a very high efficiency in this direction at a very low, what we call transversal mode level. So we have high spatial coherence. The third aspect is a frequency selection. We call those longitudinal modes. And this results in a very narrow line width, and that's what we call temporal coherence. Let's start with this temporal coherence and with the formation of modes. Longitudinal modes result from the fact that in between the two mirrors, here they are indicated just by these bars, in the case of high reflectivity, we follow from the Maxwell equations that the electromagnetic field is zero at the point of reflection. And that gives rise to a boundary condition in terms of the phase of the resulting waves. If we are bound to the fact that the electromagnetic field vanishes at these surfaces of the mirror, we can have one mode of oscillation in which we just have half a wavelength as a resulting wavelength. We also can have a full wavelength, or we can have 3 halves, or 4 halves, or 5 halves, but it's always a multiple of half a wavelength. And that results in allowed frequencies. And if we look at the frequency spacing of these allowed frequencies, they are equidistant, and the distance, the frequency distance, is C over 2L. C over 2L, a very important number in resonator analysis. So, as an example, if you take a CO2 laser with a wavelength of 10.6 microns, the speed of light 3 times 10 to the 8 meter per second, and a resonator length of 1 meter, the resulting frequency spacing, delta nu, is 1.5 times 10 to the 8 hertz, 150 megahertz. So it is a value which is way below the wavelengths or the frequency of the laser. The frequency of the laser itself is somewhere around 3 times 10 to the 13 hertz at a wavelength of 10.6 micron. If we compare this frequency spacing of the longitudinal modes, and here in this frequency spectrum you can see the spacing. The spacing, delta nu, was, as you remember, C over 2L. That's the spacing of the frequency. And usually this spacing, depending on the resonator of course, is much, much smaller compared to the line width of the active medium. The blue curve is the gain profile of the active medium, and usually we have very many longitudinal modes allowed under this curve of the amplifying medium. Actually, the theory for analysis of this effect has been given long before the laser was invented. 2 French people did that, Fabry and Perot. The so-called Fabry-Perot resonator simply shows 2 mirrors, and actually their theory was designed to explain the multi-reflection of thin films. So they wondered how the contributions of an individual reflected, transmitted part, which then again will be transmitted or reflected, how that sums up. So they analyzed the individual contributions from each reflection. This is shown in this sum here. And then if you look at the limit and solve this series, then you come to the expression for the transmitted intensity as a function of the incident intensity I0. And the only parameter which is in here is the reflectivity R. And a phase, but this is usually negligible. If you look at the geographical solution of this equation, if we plot it, we look at the transmission versus basically the frequency. In this case here, the phase in numbers of pi is plotted, but this is actually the frequency spacing. And you can see for small reflectivities of the order of 0.1, we get a very intense modulation due to the resonator. So we have, for phase matching, we have very high reflectivity and transmission. And in the case of non-phase matching, we have very small transmission. So the resonator filters very efficiently these wavelengths, again at a frequency spacing of 2C over L. Needless to say that for lower reflectivities, here in this case 0.1, the green curve, the modulation is very shallow. In the limit, if R goes to 0, the reflectivity of the mirror goes to 0, which simply means there is no resonator. We would just have a straight line, and again, of course, all frequencies will be allowed. As a first intermediate summary, a resonator is a very precise filter for longitudinal modes, that's frequencies, in a laser. And the higher the reflectivity of the mirrors, the deeper is the modulation and the sharper is the filter with respect to the resulting frequencies. This mode selection, as I said, usually is much smaller than the spectral width of the gain medium. Again, in this picture here, we summarize what we have seen so far. So there are individual longitudinal modes depending on the resonator geometry, C over 2L, and where L is the resonator length. And usually a lot of these longitudinal modes go under the gain curve of the laser medium. Let's talk about resonator stability next, before we come to the transverse modes, the transversal modes. So stability in this case here is defined, maybe you see it easiest in the right-hand picture. If you, so to say, make a schematic display of a resonator in which you substitute the reflecting mirrors with certain radii by lens and look at, so to say, you unfold the resonator reflection for reflection, reflection by reflection. So then you can see if the reflection reproduces itself in terms of geometry, and so to say the beam stays in the resonator, then we talk about a stable resonator. In the case the resonator is formed such that the resulting beam moves out step by step out of that system, the resonator is called unstable. In this picture here you see further examples of corresponding modes. Again, each of these dotted lines represents now the position of a reflecting mirror, and not necessarily the beam needs to reproduce itself after 1 or 2 reflections in the resonator. It can happen that you have maybe 5, 6, 10 reflection and then only come to the same path again. Still, this would be a stable resonator. Or in the other limit, as soon as we have an increasing, accumulating displacement of the beam in the resonator, then sooner or later it will leave the resonator and go out of the system. That's an unstable resonator. Again, it can be oscillating between first sight positive boundaries, but still, if the intensity or the displacement increases with each reflection, the resonator is called unstable. If we now look at the theory of resonator description, we use a trick. We ask for such solutions that by definition are stable in that resonator. On the left-hand side you see the general formation of an eigenvalue problem. In this eigenvalue problem you see the same function em of x and y. Same thing. So we have a certain operator b. In this case, operator b represents the reflection of the radiation at one mirror number 2, then another reflection on mirror number 1, and 2 traveling paths. The beam needs to come from 1 to 2, so there are 4 processes: travel to 2, be reflected at 2, travel back to 1, be reflected at 1, and then this is the full loop. Now, if we say we look for functions which reproduce themselves under this operation of these 4 steps, then we formulate it mathematically. The process of traveling and reflection is summarized in this matrix B. That is what we do to an initial field solution EM, and we look for solutions which reproduce exactly the same E after application of the 4 passes, the 4 steps, and then we look for the same solution, however just varying by maybe a little in magnitude. So gamma is simply a scalar number, so we allow maybe for some diffraction losses here at the edges. But in principle, the function shall be an eigenvalue, shall be an eigensolution of this eigenvalue function. The physicists among you may know the analogy in the Schrödinger equation, which also is an eigenvalue problem. So it's a trick that we frequently use in analysis of physical systems. If we do that on an integrative form, you see it here. We collect all the contributions due to scattering and reflection and traveling. Again, have the eigenfunction which is reproduced, same function at a point 2, just varying by a scalar factor. If we look at what is happening, if we start, for instance, with a rectangular distribution and go through individual apertures, think of reflecting mirrors of a certain size, then we know from diffraction that this initially top hat profile will change due to Fresnel diffraction to some complex shape. Then we come to the next aperture. It cuts out only the center part. Again, this will then be subject to diffraction, and so on and so on, and ultimately we will end up with a solution which looks like this. It's a Gaussian shape, and this Gaussian shape will of course be cut off at the boundaries where the aperture or the reflecting mirror can be thought, and then it reproduces itself after a certain number of passes. And that is the eigensolution of this resonator. So if I start this simulation of the resonator now, you see it starts with a Fresnel number 1, so we have 1 peak in the center. I put in 5, so now we have 5 peaks to start with. Then I take 10 turns in the resonator and let the simulation start. You see, diffraction by diffraction, it approaches the Gaussian profile until after about 50 to 100, depending on the resonator, passes through the resonator, we will have the eigensolution in form of a Gaussian beam. You can play with this simulation yourself. You see the web link under which you can directly link into the model, which you actively can program and look at the diffraction as the stable form of the eigensolution will form. The result itself is seen in the next slide. It's a Gaussian beam, a Gaussian mode. We call it the eigenmode of a stable resonator. It has the typical exponential square dependence on the axis perpendicular to the axis of propagation. So, like you've seen in the pictures before, you can imagine this Gaussian shape like this. And here you see the position of the 2 mirrors, the formation of that eigenmode, which is a Gaussian beam. If we look at the higher order modes in the transversal mode formation, it is always a Gaussian mode E Gauss as printed here. You see the classical function, the Gaussian distribution. But now in the next first order, it is multiplied by a Hermite factor H1 for the first element in the series development. If you multiply these 2 functions, then we get this function here. If we square it to get the intensity from the electric field, we have 2 peaks as a function of the radius of the beam. The next order would be a square Hermite factor, so that would be a parabola, an x square. If we multiply the x square with the fundamental mode Gauss, then we get this type of distribution. Again, square the result, we get 3 peaks, or a ring with a dot in the center if we think of radial symmetry. Radial symmetry is not Hermitian modes, but Laguerre-Gaussian modes. Same thing actually. The first order results in a peak and a ring, the second order in a peak and 2 rings, and so on. So in transversal mode selection, which has a lot to do with diffraction, it is very similar to diffraction. We have the 0 order diffraction, so to say, is a Gaussian beam. The next higher order is 2 peaks, 3 peaks, and so on and so on. So we have a lot of higher order modes, and usually in high quality laser materials processing, we select only the fundamental mode, the Gaussian TEM00. TEM stands for transverse electromagnetic wave. Here in this next picture, you can see a plot of the higher orders in X and in Y. So 0, 0, 0, 1, 0, 2, 0, 3, 0, 0, 1, 0, 2, 0, 2, 2, 3, 3, 4, 4, and so on. You can combine all kinds of orders in different directions of the beam. In spherical symmetry, we learned that we use the Gauss-Lagrangian modes as solutions, and again you get the radial dependency, so to say, the radial interference in one direction, and since the other coordinate is an angular coordinate, we get an angular separation, first order, second order, third order, and so on. This picture actually summarizes the situation of the resonator. If you look in a so-called stability diagram where are plotted 2 G parameters, and the G parameters are related to the characteristics of the individual mirrors in the resonator. So G1 is 1 minus length of the resonator, distance of the 2 mirrors, divided by the radius of the first. So it's a dimensionless magnitude, the G parameter, and for each mirror you have one value, for G2 correspondingly. And if we now plot G1 versus G2, you see here 1, 1, a point 1, 1, and G equals 1 would mean R equals goes to infinity. So that is a plane mirror. A plane mirror would have radius infinity and would have a G parameter of 1. So in this diagram, the point 1, 1 corresponds to a plane resonator as seen here. And it is obvious that a plane resonator is at the limit of a stable area to an unstable area, because imagine a beam going back and forth in this resonator. It has to be ultimately precise if it would not leave the resonator after a certain number of passes. So this is a limit, a case in the limit, which is the reason why this point is at the boundary of the stability region, which is this part of the curve, and the non-stability region here. Due to symmetry, we have the same thing in minus areas of G, G1 and G2. Now, here in this top picture, you again see the longitudinal modes with their separation of C over 2L. And you see also drawn in here further smaller lines. Those are the shifts in frequency if we have higher transversal mode. So for a certain longitudinal mode, TEM00 transversal mode, this is the frequency. If we have a higher transversal order, 1, 1, for instance, then we will have a slight displacement of the frequency, which can be explained by the fact that the resonator is, so to say, a little tilted. Now, if we make a virtual journey along this path here over different resonators through the stable region, what happens is that first we come to this second point of interest, which is a symmetric case. It's a confocal resonator with G1 equals G2 equals 0. And if we continue, then we come to a concentric resonator at the other end of the stability area before we get into an unstable area. This picture again shows now both. It shows the longitudinal modes and it shows the higher order transversal modes as the slightly separated shifted lines. And the whole thing again now is enclosed or is underneath the gain curve of the medium. As I said before, usually we have many modes under the gain curve. However, if you now look at the laser's threshold, so for a certain value we have enough gain in this amplification medium that the modes really will start to oscillate, and then everything which is above the threshold will result as a frequency of emission of the laser. So in this case here we will have 4 longitudinal modes in the emission spectrum of that laser, 4 wavelengths at a certain longitudinal mode. Of course now we can optimize the situation depending on what we want to do. If we want a single mode laser, we would, number one, could narrow the gain profile, which is pretty difficult. It probably is easier to increase the separation of the individual modes, and as you remember, the frequency spacing here is C over 2L, so all we need to do is increase L, then we decrease delta nu, or other way around. If we decrease L, we increase delta nu, the mode separation. So short resonators will lead to a larger separation of these modes, maybe all the way until we have only one mode left under the gain curve. So only this mode will start to form and we will have no further oscillation at different wavelengths. The opposite would be we make really long resonators and have very wide gain media. Then we would have a lot of longitudinal modes under the amplifying profile of the medium, and that would be wonderful for mode coupling to generate ultra-fast lasers, femtosecond lasers and picosecond lasers by mode coupling. So to summarize this video on resonators, I just want to recall the 3 main tasks, roles and characteristics of a resonator. Number 1, it feeds back by reflection the electromagnetic energy into the active medium and keeps the stimulated emission running. It's the optical feedback. Number 2, it's the selection of longitudinal modes. Longitudinal modes are the ones with different frequencies. The frequency spacing is constant, and you remember the value C over 2L. The third property is the transversal mode selection. We have a fundamental mode, which is a Gaussian mode, and we have higher order modes. For each order, you just can add 1 maximum in the diffraction pattern. And now, finally, let's look at some actual resonator examples. Here you see a gas laser. It is an argon ion laser. Maybe you can see these Invar rods here, which stabilize the plates in which the resonator mirrors are mounted. Here's the one mirror. The other one has to be imagined on the other side. Another example of a gas laser is the helium neon laser. This is a very tricky resonator because it has no external resonator. We use the gas tube as a resonator suspension and just melt and solder the mirror onto a metal holder. This metal holder is connected to the glass tube, so we have a monolithic structure, and the resonator is mechanically stabilized simply by being soldered onto these mirror mounts here, and the mirror itself sits here at the end, right at the end, and the adjustment is just done by displacement of that mirror. This is a soft metal, so it just can be bent a little, and so we adjust the laser, and that's it. So very straightforward, very simple way of setting up a resonator. In solid state lasers, usually we have separated mirrors. You can see one mirror here on a specific mirror mount, the active medium with the pump and the cooling in the middle. And diode lasers, that's a special case where you cannot see the resonator because everything is on the nanometer scale. The resonator is directly integrated into the light emitting bar, which is about that size, very, very small in the case of a diode laser. And we have no external resonator, just cleaved and coated ends of the gallium arsenide semiconductor active medium.